Databricks Developer Relations. Prior to that, I have been designing and building data platforms in large sort of multinational corporations. And just this morning, I had an experience. So I spent the better part of this morning waiting behind a garbage truck in the narrow streets of Paris, trying to get here. And this could have easily been avoided by just kind of going around the corner and being picked up somewhere else. But for these systems to be smart like that and make decisions like that, right, they need access to information that is much different than the information we offer to them right now, right, sort of the classical tabular information. And today we'll talk a little bit about what are some of the challenges that we see with kind of these new workloads, and what are some of the, well, so you may be leaving here with more questions than answers, so sorry for that beforehand. But some of the things going on in the larger data ecosystem, how we might address some of those things. So one of the biggest challenges that we see is that the nature of data being processed is fundamentally changing in volume, but also in quality, right? So in traditional systems, we could always kind of structure the data in tables, sure, sometimes on write, sometimes on read, but ultimately data was structured with columns, fields, nice data types, all of this kind of stuff. But in the AI world, in the multimodal world, we're shifting more and more towards videos, audio, images that, from a data perspective, are just large, like blobs, binary large objects, right? And we need to process those at scales and speeds similar to what we could achieve with the traditional data stack, right? So here are some numbers, projections, whether they're true or not remains to be seen. But what we can say is that this is increasing at a very high speed, right? If you take traditional platforms like Reddit, right, all text-based, fairly easy to process, and then you have something like TikTok, where it's all videos, and you want to query those videos, you want to index them, all of this, obviously very, very different kinds of workloads. So the question is, do we evolve existing technologies, or do we create entirely new ones in order to handle this kind of stuff? You may know the answer already. It depends, and we'll probably have a mix of all of this. But let's explore a little bit of what that might look like and what we're seeing today happening in that space. So I myself, I really like file formats, table formats, all of this kind of stuff. And all of these icons may or may not be familiar to you, right? So we started in the early days of MapReduce with the sort of Hadoop stack, Hive, Parquet, ORC, Avro, were then built as file formats that address some of the challenges that we've seen on there. We then layered on top of this table formats, Iceberg and Delta, that were able to handle huge collections of these files and scan them efficiently. And one of my favorite technologies, Arrow, I just had to put that on there because that's sort of the in-memory representation of data. And all of these technologies have been incredibly successful, but we have to do something to adopt those to the multimodal workloads we see today. So, looking into open table formats. Open table formats, in principle, you can use today in order to, binary data can be stored today in Parquet files, right? It's just a bytes column, it's fine, you just put it in there. However, blobs are much, much larger, and there are some challenges just due to the nature of processing systems, right? So internally, these representations use something called offsets, which is 32 or 64-bit integers. And if we are trying to take a, I don't know, commonly used record batch, I don't know, 1,000 records, 10,000 records, and then we try to shove, I don't know, videos, each a gigabyte or a couple hundred megabytes in there, we're just kind of hitting the limits of these systems, right? So another approach is what sometimes is referred to as column of URLs. So you just kind of store references to all of these files in your columns, and then you somehow need to treat those references as you process them, right? And you can store metadata of these, so you can try to index these files first in order to, so you can try to store some metadata, index all of this first, but that's not necessarily what you want to do. There's one interesting thing going on the Iceberg format. There is a file format API, just mentioning it because it becomes interesting what this essentially aims to do, and it's not doing that just yet. But right now you're allowed to store your data in Iceberg tables as Parquet, Avro, or ORC, sorry. And the file format API tries to abstract some of this. And we'll talk more about what some of these abstractions might look like. So, going forward, there is already something happening that's great. And to me, from a community perspective, one of the great successes of recent time. So the variant data type. The variant data type is a means of storing semi-structured data in a way that you can efficiently query it and store it also kind of in terms of size efficiently. So traditionally, JSON data would be serialized as strings or serialized as sort of raw bytes, but every time you read it, every time you want to query a field, you need to go in there, you need to parse everything. Parsing is expensive to extract stuff. The variant data type, and why do I think this is one of the great successes? Because it's so useful, everybody wanted it. So there was almost no discourse amongst the different parties and vendors out there in trying to get it into the specs. And this type, you can actually store it today, and you could have implemented this on the Spark side, for instance, only, right? So only Spark knows what variant is, and variant materializes as simply two binary columns. So everybody could have read this, but the file would have been meaningless. So yeah, variant data type, the community was able to actually push this all the way down to Parquet. So I think it's accepted part of the Parquet spec now. And this solves one piece of the puzzle. It solves how do we deal with evolving semi-structured data that we want to store in there, right? But this doesn't solve the blob stuff. So what are some of the challenges around blobs? So blobs, again, as a reminder, binary large objects. This is how we represent videos, audio on disk, right? And you could shove this into a table. You could shove it into a Parquet file in a binary column. But again, there is constraints on this, just what the machines can physically handle in order to process this data, right? So again, with the offsets, I'm not going to go into this again. But suffice it to say, either you go very small in your processing size, processing only 2-3 rows at a time, right? If you imagine, let's say, the 2 gigabyte video files, you can't give an unlimited amount of memory to your processing engine and just say, okay, just load it all, right? So your workers all have, I don't know, terabytes of memory. That's not a feasible or economical approach. So the other thing is you could slice your pieces of work so small that, I don't know, you just process 2 or 3 rows at once. But then you lose all the benefits we've been working so hard to get with vectorization and SIMD and all of this kind of processing, right? We would lose all of this. So that's really not a feasible approach. And one of the challenges here is that engines are simply unaware that this sort of blob exists, right? When they see a binary column, they assume something like UUIDs, right? UUIDs you can also represent as bytes. It's 16 bytes, nice little bite-sized chunks. But with blobs, obviously, this changes fundamentally, right? So, and who doesn't love the OOM, I don't know, worker out of memory sort of arrow digging through Spark stack traces or what have you. So, what are some of the things that should happen in blob-aware processing? First of all, laziness. Let's not try to load everything into memory at once, but let's try to load it as we need this data. And there, a fundamental thing that query engines have been doing all the time is a problem, which is if you, let's say you want to create an embedding for your audio file, or you want to downsample it, or what have you. What the query engine would do is materialize all of this, your, I don't know, embed UDF that invokes your PyTorch model or your external OpenAI API, however you want to do your embedding, would get the entire payload. But oftentimes you just want to look at individual frames maybe with certain offsets, right? You may be only interested in scanning the first couple of seconds or minutes of a video. So there, again, this sort of laziness should come in, and these functions should receive handles, either stream handles or something. I don't want to say file, because we've been working very hard to get all of these HDFS file system aware semantics out of those systems. So let's not call it files, but some sort of handles sort of to stream that allows some more tailored processing for these workloads, right? And then the planning that these engines do, imagine a shuffle, right? Imagine a shuffle. Again, we have our 2 megabyte video, and now the engine says we need to do a join. So we'll start sending those gigabytes of data through our cluster, through all the workers. Also not a very good idea, unless you're a hyperscaler and you're selling the network bandwidth, then it's a great idea. And also stats are not so meaningful on blobs as they are for other columns, right? So we may need to think about how do we collect stats, how do we represent this data so that engines can reason about it better. And the reasoning, I don't know, a colleague of mine said is, okay, you do rocket science first and then you start query optimization. So it's hard. Query optimization is hard, and having meaningful stats and meaningful information about the data you're loading and reading is imperative here. So what are some of the things that are happening in order to address this? There is hybrid storage models that people are looking at, kind of inlining some of the data that you require directly, and then processing some stuff out of core. Yes, obviously that's a nice little retro effect I tried to build in there. So one thing that I find interesting, and this is again, are we evolving stuff or are we creating new stuff, right? So there is something called the blob space concept. Blob space concept is very, very interesting, but also comes with some challenges. It essentially says you build up this, well, object store, right? And you just store all of your blobs in there. It's again a formalized version of the columns of URL kind of concept, where you also try to avoid copying the data between different tables by just having pointers point to this. But there are some challenges, and some of the challenges we'll may be able to address by everyone's current favorite topic, catalogs, right? Because some of those files might be orphaned, right? So if multiple tables reference the same thing, how do you make sure it gets cleaned up at the right time? How do you enforce governance or access permissions on this sort of blob space kind of concept? And this is what the community is working on right now, what they're looking into. How can we make this a reality? There's also other very interesting concepts, entirely new formats, right? So I think a lot of this was sparked by something called fast lanes, which is a new kind of encoding for data, kind of very low level, several layers into Parquet. You encounter something called encodings. And people have been looking into how do we leverage this kind of stuff. And some of my favorites are Lance, is a new file format designed for multimodal workloads. It's designed to handle embeddings very, very efficiently, which is kind of just fixed size arrays, but also other kinds of data. There is Vortex, which is a very interesting concept, and I have people here also talk about doing the same for Parquet. Essentially, Vortex allows you to embed your encoding as a WebAssembly directly into the file. So rather than saying, I don't know, you need to know what run length encoding is, it says, no, here, load this WebAssembly, load it in your runtime, and that thing just knows how to decode it. There is a little bit of trust issue, right? who wants to execute unchecked code in their kind of potentially, see, it's a sensitive environment, but still, there is means how we can verify this and make this sort of thing work, right? And they have many other improvements that help with these kind of workloads and data. So, but having specialized formats is not the only thing we can do. We can also leverage specialized hardware. This includes kind of, everybody knows a CPU and GPU. I don't know, modern cell phones usually have something called a neural processing engine, which is just another architecture that kind of mimics this, I don't know, expand, contract structure of neural networks, right? Where you fan out, you compute a lot of weights, and then you have your aggregate kind of steps, min-max, soft-max, what have you, things. And then these modern architectures kind of mimic that and are specialized for this kind of compute. And I want to mention one interesting engine, which is Daft, which is the first engine I'm personally aware of that does, let's call it blob-aware scheduling, right? So when you load something during runtime, traditionally all the operations that you perform on data, I don't know, plus, minus, module, or whatever you can imagine, whatever you can express in your SQL query, would something that's CPU bound, right? Where you're not waiting for anything to happen, you're not waiting for network latency or anything, but you can just, your CPU is kind of busy doing work, and you can just, well, congest is the wrong word, but you can fill all the work units you have with the work. If you're invoking a function that tries to invoke an external API, like an embedding, if you're loading data remotely, that's, I forget the words, it's concurrent and parallel, was it that? So essentially, you need to wait for stuff, right? Whenever something is I/O bound, you're just saying, give me that thing, and then you wait until it arrives, but you have nothing to do until it arrives. You could well be doing other stuff. And Daft is aware of which operations are I/O bound, and interestingly enough, executing something on the GPU from the query engine's perspective, which runs on the CPU, is kind of an I/O bound task, because you're pushing some data to the GPU, and then you wait until the GPU kind of puts the result back into memory, so you can read it from there, right? So this specialized hardware and task-aware scheduling is something that's very, very interesting, and I think it's going to be kind of a piece of the puzzle. All of this raises the question, so are we now going to just hyper-specialize on every sort of niche case, right? Are we building formats that are, I don't know, tailored to very, very individual tasks, or where do we strike the balance between all of this? Again, I don't have an answer for you, but maybe a perspective, how can we look at this? And as I mentioned earlier, I come from the platform kind of design and build space. And one of the things, pardon, one of the things I used to say there is, don't try to build the platform you want to build, just build something you can change and adopt quickly, right? Optimize for evolution. Don't optimize for the perfect end state, because you don't know what that is anyway, and when you get there, it's probably, it's going to be a moving target always. So this is a picture I like from the folks at HopsWorks. From the folks at HopsWorks that try to kind of highlight which parts of the Lakehouse need to be adopted for the AI era. Personally, I feel this is great work, but we just talked about, we also are adopting both table and file formats. We're also working on the catalog level. If we're being honest, we're also working on the engines, and this is not my forte, but BI tools are also evolving quite quickly with natural language interfaces. All of a sudden, you need to deal with kind of all of this generated SQL. How do you So we've been building semantic systems for many, many years, right? But semantic systems that assumed a human is looking at that has some kind of baseline knowledge about the world. If we present semantics, context about data to an agent, we need to be much, much more explicit about many, many more things. So also these layers are evolving quickly. So how can we design for evolution? The good thing is we don't need to come up with this. This has been done before. There's two patterns I personally like to think about, and they're not necessarily radically new, but I think it helps to think in those terms and remind yourself of kind of what they are. One of those is the Lakehouse. Lakehouse, we all know. The other one is composable systems, essentially a destructured query engine. So, first of all, we are moving to a catalog-aware architecture. And from the table formats perspective, Iceberg has always been a catalog-aware architecture from day one. Delta has not, but is becoming catalog-aware in a sense of it knows there's an ever-present catalog, and with that you can also do other cool stuff like multi-statement transactions, multi-table transactions. All of this goodness you can execute if you have a catalog. We also need to track, though, more assets, right? Tables and views are no longer enough. We also need to track, for instance, UDFs. UDFs sounds boring, but in many ways today you can also call them tools, or you can put them behind an MCP. Then they're cool again. You still need to track them. You still need to manage those things and be able to provide sort of a consistent view of this to all of your users, right? And you also need to, again, provide more explicit metadata to the agents so that they know how to use these tools, right? And then we have something, so let's go a little bit deeper into composable systems. And here I take one of my favorite projects, Delta Kernel, but just imagine that it's just kernel and not Delta Kernel, because the main purpose of this is to not be specific for one table format, one engine, right? And what you see here is this n.m complexity. Essentially, every engine needs to implement every feature of a table format. And we've seen this with variant type, we mentioned that, right? Iceberg got deletion vectors, row tracking, but there's many, many other features out there. But we don't want them only in Spark, we want them in DuckDB, we want them in Polar, we want them all over the place, right? So the traditional architecture of an integration on an engine level used to kind of say, okay, here's the engine, here is my trait, my abstraction, a table provider, what have you. You implement this, but this meant one engine-specific sort of implementation that all need to be maintained throughout the architecture, right? And we talked about file formats before. I don't know if anybody looked at, let's say, a Data Fusion's Parquet reader. Well, that thing is a beast. You can squeeze so much performance out of this. It's incredible, but you don't want to maintain a lot of implementations of those. And you certainly don't want to maintain this if you just care about sort of the table format. Right? So, very easy. Let's just embed this into the kernel, into the engine. And I need to hurry up a little bit, so the next part is a little bit dense, but let's hope it makes sense anyway. So, what does the kernel architecture look like? First of all, you need to agree on some interfaces, on some APIs, right? And some of those APIs are fully known to kernel. For instance, the schema. The schema is part of a table specification, right? It defines what kind of data types can you store. I don't know, all of this information is kind of very explicit, and we need to track it explicitly. Then there's expressions and predicates. A kernel doesn't want to evaluate those, that's engine responsibility, but it needs to write some expressions. And here the implementation is very interesting because everything that the engine needs, or the kernel needs to be able to write is explicit, and then there is this thing called an opaque expression. And an engine is free to push anything in there, and can it still use it for file skipping and all of this kind of stuff. And the engine fully controls what the implementation looks like, right? This is kind of just passing around pointers between the engine and the kernel. And this works really, really well. So we do this very actively with DuckDB right now. This is an ongoing project. And you may know sort of the schema is fairly small in size. Expressions, especially expressions generated by BI tools, are notoriously large, right? Several megabytes. The largest, obviously, is the data. I mentioned Arrow before, but Arrow is not the only data representation out there, right? DuckDB has its own representation. Vortex, I think, has its own representation. I forgot what the meta... Anyway, there's multiple representations out there, and kernel can't dictate what data should look like, but needs to reason a little bit about this data. But this is completely opaque, right? So now, let's try to make this a little bit more concrete and look, so we're inside the engine, right? This little thing here, this is our kernel. So let's see, how would it look like if we have a query and we resolve that into a response. So first thing, the query, there is some translation going on, but ultimately you point to some file where you want to read the data, or some location, a folder maybe, where you want to read your data. So then, kernel goes ahead, and this is specific to Delta, but the logic is the same for Iceberg, for instance. Just looks at that file location, does a list, I don't know, read some bytes, gets a file listing, and here is where it gets interesting, right? The important part is we leave the kernel all the time, right? So we call back into the engine and say, read what you find in those files, in those JSON, Parquet, what have you files. And the important part though is, and the color coding here is important, right? So red was kernel knows what it is, whereas blue is, kernel has no idea what that thing actually is, whatever the engine decided to read out of those files. So kernel can't directly probe into this, right? But then kernel takes the predicate and says, here, take this data, and it has some idea of what the shape of this data is, the schema of this data is, right? And evaluate this predicate on top of this, please. Then it gets back what I call kind of the unresolved logical plan. A schema, it should read from the data some expressions, it should apply to it, and the expressions are very, very important. It's essentially many features can be just expressions. I don't know, partition values, column mapping, all of this just expressions. Then you optimize it, execute. One exciting thing I'm going to mention, time is up, but Rust for the win, I'm a big fan. We also working on actually putting this into the JVM, so there will be one single implementation for the entire ecosystem. There always used to be this break between native and JVM, but we're hoping to bridge that gap. All right, thank you so much.